amount of time. So during this entire this 50 milliseconds, you also have to keep track of the encoder of your motor, okay? Because you want to keep track of how far the wheel has turned, so you can keep track of your location that way. And let's just say that you're doing that requires 1 millisecond. Every 1 millisecond, you have to keep track of. You have to read the encoder feedback from your motor, and this is not even close to 50 ticks here, but we'll just kind of imagine there are 50 ticks per 50 milliseconds. Okay, so let's just focus on this part here. So just 2 tasks to perform: video processing and also keeping track of the encoder of your motors. How would you do this when you can only use one single thread and one single process? Yep.
You have your video frame set up so that you will call a function that will run for a maximum of n milliseconds, and return storing its current state so that then can we call it using
Exactly. Okay? Exactly.
I think that would be annoying.
That would be annoying, but that's how people do things. Okay? Yeah, that's how people do things when there's no support of multi-threading or processes. Okay, so let me just kind of re-emphasize what you can do to make this work. You are only allowed to use one single process, and inside that process you're only allowed to use one single thread. So, and you cannot use interrupts. In other words, you cannot set up an interrupt to interrupt every 1 millisecond to basically give you that 1 tick count. So in order to do something like this without interrupts, without an operating system, without any processes, with one process and one thread, what you need to do is in your process video subroutine, okay, so this is the process video subroutine, you basically have to break up the processing of the video frame into small chunks and make sure that each chunk will take less than 1 millisecond to perform. So it will perform one chunk here, and then it will scan, it will read the motor encoder to do something about that, and then it will perform another chunk here, and then you'll check the motor again, perform another chunk here, and then you'll perform the motor function. Okay? Now where you left off right here needs to be picked up by this point here. So the state of the video processing has to be saved somewhere, inside the structure or something else, so that you can resume the operation after dealing with the motors. And this is basically chopping up one long task into smaller chunks so that something that has to happen more frequently can get to execute at the frequency that it needs to execute. Are there any questions so far about what I'm trying to illustrate here? Okay. Now, if you look at a robotic application, or maybe not just robotic, let's just say that you're dealing with a car application. Okay, your car has multiple computers, and many times those computers also have to keep track of many different things. It's not realistic to just say that there are 2 different things that your processor will have to deal with at any particular time. It could be 5, 6, 10, 12, 20 different things that it has to do all at the same time. Some may be high priority, some may be lower priority, which means the lag time or the latency time of the modem, your modem monitoring may be very little. Okay, you can be off by say 50 microseconds, but no more than that. But as far as frame processing is concerned, maybe plus or minus 10 milliseconds won't hurt anything. Okay, but this is painful because every time you add something to this whole thing and say, okay, I also have to perform, let's say, GPS processing every half second or so, you have to stick it somewhere within this loop here. Okay, and it just complicates things as you try to add more and more and more tasks, but they have to be chopped up in order to maintain the frequency of the things that you have to execute at a higher frequency. Does everybody understand? Yep.
What about when you change processor frequency?
When you change processor frequency, then you have to rework all these things. In other words, before you use a slower processor, and the video frame you can only process, let's say, 1/4 of the frame. Then you have to run the encoded code, and then you continue with the video processing. If you change the processor speed, then you may be able to process half a frame, before you have to give up control to run the motor thing.
say, for example, you have a faster one, then aren't you going to suddenly throw all the tiny stuff off? Or
It will just throw everything off. Exactly. It will throw everything off because then your motor, it will basically sample faster than you have to. Okay, now whether it's okay to sample faster than you have to is also another question, because it depends on whether your wheels, the encoder and whatnot, can keep up with the frequency that you're sampling. So you're definitely bringing up a very good point. As soon as you change the hardware characteristics, the timing of this entire thing is thrown off, and then you have to retune the whole thing to work the way it is supposed to. Okay. Is everybody kind of understanding the complexity of doing things this way? Okay, I'm hoping. And this is how micro mice are usually done at UC Davis. Yeah, it's really bad because they have exactly all those tasks to perform, because a micro mouse has to do many different things at the same time. One, it has to control the wheels, or basically the motors, so they control the speed of the motor to speed up, slow down, and stuff like that. It has to look at the sensors. Okay, the sensors typically point to the side like this and point to the front like that. So it has to map the walls. It has to see whether, okay, am I seeing a new wall? If so, I have to add it to the map. It also has to do error correction. If it's too close to this wall, it has to skew just a little bit to make the corrections. It has to run the AI algorithm. Okay, if I discover a new wall, I have to rerun the AI algorithm so that I know, should I turn around, should I make a right turn, should I make a left turn, because the path would have changed, when you discover a new wall. So all of those things also have to happen at a particular frequency. Some are dictated, by hardware, some are dictated by, software, and some are dictated by, just, how fast can you run it. So it has all these problems, exactly the same way as what we are talking about here, and most micro mice are without any processes and without any threads. So that makes the program a little bit hard to deal with, because you have to sprinkle, things to control the motor, things to control the mapping of the walls and whatnot, all over the place. And it just becomes a beast to maintain, once you have added enough stuff to the logic. Okay? And you might want to ask, but how come they don't use a multi-threaded model and just, be done with the whole thing?
Because the device doesn't support it.
I beg to differ. The device does not have a built-in kernel, but I wrote one, and I told my students at UC Davis that there is at least 2 or 3 multi-threaded, microkernels. They don't want to spend the time to learn how to interface with a real-time kernel. That really is the bottom line.
Wouldn't it be simpler?
Oh, way simpler. If you use a multi-threaded kernel, it would be way simpler. This is about the investment of time to learn a new tool to save you time down the line, as opposed to not learning a new tool, keep using the old tool because you already know how to use it, but down the line it becomes a chore to do everything that you have to do. It's kind of like using a hammer. I have a manual hammer. I know how to use it to put nails into wood. Okay, and if you're just doing a very small project, it's not worth the time to invest in a how do you call the nail guns? Okay, because with nail gun you need to set up a compressor. You have to know how to load the nail into the machine and stuff like that. Not to shoot it at yourself, and many other things that you have to be aware of when you use a nail gun. A hammer and nails is easy, right? Just to put it here and bam, you're done. Yep.
Have you used LinksOS?
I have heard of it, but I have not used it. I know it is a commercial real-time kernel that is used by a lot of real-time devices, but I personally have not used that.
Our ultrasound we have ultrasound units.
And that's a real-time application. Does everybody understand what is a real-time application as opposed to a non-real-time application? What you just described as a sauna unit is a real-time application, because the measurement of the return of an echo has to be done with very good timing resolution. Otherwise, it would just be useless. Okay, so it's a real hard real-time application because someone can actually define and say, when the echo comes back, the timing has to be accurate